So in the previous discussion we have discussed about the scaling analysis of the boundary layer equations, and we got some approximate results. So we got something like delta by x, and that is scaling with this thing rex whole to the power minus half. So this is what we called an approximate solution, right? Okay. Now, but if I have to get something like this is equal to some k into rex whole to the power minus half. So this I will call an exact solution. So scaling analysis provided me this one, the approximate solution. So it is giving me the most important thing as an engineer, that is the relationship between the independent and the dependent variable. But now if I want to get this constant k, so then I have to solve the boundary layer equations exactly. Okay, and that was done by Blasius. Okay, so the philosophy of Blasius was, if I draw the boundary layer again on a flat plate. Okay, so this is the flat plate. Okay, and the fluid is flowing like this, having a velocity u infinity. Let us first choose our coordinate system like this is x, this is y, and the boundary layer is forming like this. Okay, so at any section we have a particular boundary layer thickness. So the velocity profile at this section can be given like this. Okay, and at any other section the velocity profile will be different, and we know that here at the same y the velocity will be lesser. Okay, okay. So if this is section A and this is section B, then I have a particular boundary layer thickness at section A, and which I will call as delta A, and that at section B I will call as delta B, right? Now we have some similarity between the two velocity profiles at section A and at section B. Okay, intuitively I can say that it seems that if I can stretch the velocity profile of A, then I can get the velocity profile of B. The concept is like, if I am having a triangle, right? So maintaining the same angles, I can stretch the triangle or I can shrink the triangle. And this concept in geometry is known as similar triangles, right? Similar triangles. Okay. Likewise, I can stretch this this velocity profile at section A to get a velocity profile at section B. It seems like that. Okay. So from this concept, Blasius did what? So just see it that, let us say that at any y, I mean at x equal to at A, okay, at section A, okay, at section A at any y, okay, I have a particular velocity, let us say u y. U is a function of y here, so maybe this y is y1. Okay, so this is maybe y1, so this is y1. Okay, this is y1. So this is uy1. Okay, so let me write it with a different color. So okay, so this velocity is uy1 at a, okay, subscript a maybe. At the same y, if I am having a velocity that may be u at b y1, okay, okay. So what I can do is I can define a new variable f that will be equal to u by u infinity, okay. So then throughout this y, this f will have a range of 0 to 1, right. F will belong to 0 to 1 for y that is belonging to 0 to delta, the boundary layer thickness, right, because the maximum value of u is u infinity and the minimum value of u is 0. And if I scale y with, if I scale y with some uh, some variable, okay, eta, I am defining eta equals to y by, okay, so let us say delta, that is the boundary layer thickness, and that is obviously a function of x, okay. So if I do this, then the range of eta will be again 0 to 1, right. Now if I am considering this y1, then for section A and section B, this height y1 is same because that is what I have taken. But if I will consider, that is, if I am considering, let us say that I am plotting uh, here u versus y, u versus y. So at section A, my u versus y will be something like this, okay. And at section B, my u versus y will be something like this. Sorry, so let me draw. So this is u infinity. This should be same for both section A and section B. Okay, let me draw it with another color to have a nice contrast. Okay, so now for section A, the velocity profile will be something like this, and for section B, the velocity profile will be something like this, okay, okay. So this is for section B, this is for section A, okay, this is for section A. But now if I draw something like eta versus, if I draw eta versus f, okay, so both will have the same range eta and f for at both at section A and B, okay. So if I consider the at eta equal to 1, we have f equal to 1, okay. So at eta equal to 1, we will have f equal to 1 according to this definition of eta and f, right. So this is this, okay, and maybe this is this, it is 1, and this is also 1, okay. This is 0 comma 1, sorry, 1 comma 0, and this is 0 comma 1, okay. So now as I have normalized both the things, because you see that for at section A at y1, at y1, if I say that, then eta A is equal to y1 by delta A, and eta B is equal to y2 at delta B. So it is seeming that see, at eta A, delta A is less than delta B, right, delta A is less than delta B. So for the previous case, when we are drawing y versus u, then at same y1 we were having different velocities, okay, and also at same y1 we are having different f, because if u is different then f is also different. Okay, so at same y1 we are having different f, then if I plot f versus y, that will be different for section A and section B. But now if I consider eta, then see that the delta A is less than delta B, but here the y coordinates are same, that means delta eta A is greater than eta B. Okay, so what I am getting, at y1 this ua, okay, is less than ub, but this eta A is greater than eta B. So if I plot f versus eta, then all the velocity profiles will be superimposed into a single graph. Okay, that is, this graph is representing all the velocity profiles. And another thing is, see, u is a function of both x and y, right? But if I consider f is a only function of eta, then the boundary layer equations was having u as the dependent variable. So u is a function of both x and y, that means the boundary layer equations are PDE, partial differential equation. But now if I can represent f as a function of eta, then I will have an ODE as my boundary layer equations. And if I am able to convert my PDE to an ODE by applying this transformation, then I will say that the similarity solution exists for that problem. Okay, so this was the philosophy, okay, of similarity solution. You will see this method, the method of similarity solution, in various other things, like in unsteady conduction for a semi-infinite medium, also in convection. After this we will solve for the temperature boundary layer. Okay, for the temperature boundary layer of a on a flat plate, there also we will have scaling analysis, the similarity solution method, and the integral method. So I think this is clear. I am just I will just give a summary of the philosophy. That is, we can have something like, if I stretch any one profile, then I can get any other profile if I stretch or shrink a profile. So, and that is why if I scale the variables with some proper parameters, then I can have some variables which will represent the velocity profile at any section. Okay, okay, so let me now proceed with the boundary layer equations. Okay, so my boundary layer equations. So I was having the continuity, obviously incompressible flow, steady incompressible flow. Okay, so and all those assumptions of Navier-Stokes equations are also valid. Homogeneous isotropic Newtonian fluid. Okay, so this is 0, so this is continuity, and the x momentum. Okay, so u del x plus v del u del y equal to nu del square u del y square. Okay, so I have derived these equations. Okay, so let me number the equations like 1 and 2. Okay, and the y momentum equation boils down to del p del y is equal to 0, right? So now I have defined something like u equals to f equals to u by u infinity. U infinity is the free stream velocity, and eta equal to y into g of x. So I was having a blind guess of taking 1 by delta as g, but let us see that from the mathematics what I can get as G. Okay. So my objective is, I will assume that by this transformation, okay, by this transformation, okay, equation 1 and 2 can be converted into ODE, ordinary differential equation. If I can do this thing, then I can say that the similarity solution exists. If I am not able to do this thing by this transformation, then two things may be concluded. One, the similarity solution does not exist, or these scalings are not appropriate to having a similarity variable. Here this G is called the similarity variable. Okay, similarity variable. So now I want to know that if my only dependent variable is f and only independent variable is eta, then can I convert these PDEs into ODEs? So let us substitute, instead of x, y and u, eta and f. Okay, eta is containing both x and y. So I am having okay, I am having del u del x. So that I can write as du d eta, sorry. Okay, so let me do it step by step. So this is del f del x into u infinity. Because what? Because from this I can write del f del x equal to del u del x into 1 by u infinity. That means del u del x is equal to u infinity into del f del x, right? And now this is u infinity into df d eta, because eta is only a function of, sorry, f is only a function of eta, then this will be ordinary derivative and not the partial derivative, into del eta del x. So and eta is what? Y into gx. So del eta del x will be, so this will be u into f dash into y into g dash. So this will be u infinity f dash g dash. Now I have y, but I don't want to have y, so I will replace y by eta by g. Okay, so this is my del u del x. Now let us have del u del y. Similarly, this is del f del y into u infinity equal to u infinity into df d eta into del eta del y. So this is u infinity into f dash del eta del y is g. Okay, and also I have del square u del y square. So del square u del y square is equal to del y of what? U infinity into f dash into g. So u infinity is not a function of x, g is also, sorry, u infinity is not a function of x as well as y, g is not a function of y. So I can pull them out and I can have d2f d eta 2 into again g, because del eta del y is equal to g. So this will be u infinity g square f double dash. So let me term this as, let me number these equations as 3, 4 and 5. Okay, so now let me substitute 3, 4 and 5. Okay, so 3, 4 and 5 into 1 and 2, 1 comma 2. Okay, so if I do this, okay, so u into, so u is what? U is f into u infinity. Del u del x is u infinity f dash g dash eta by g plus v into, okay, v into del u del y, that is u infinity this, right, and that is equal to what, nu into del square u del y square, that is u infinity g square f double dash. Okay. So now v is also a function of x as well as y. Okay. So I have to eliminate this v. Okay. I have to eliminate this. How I can do that? Okay. So I haven't yet used this continuity equation. So what I can do is I can get an expression of v in terms of f, eta and g from this equation, that is, let us number this equation 6, and then I can differentiate with respect to y, then I can equate that with minus del u del x with continuity. So I hope the scheme is clear to you. Okay. So then I can have v equal to what, this g square f double dash by u f dash g minus f u infinity square f dash g dash eta by g by u infinity f dash g, right, and that is equal to so let me do the cancellation process with another color. So g and 1g will cancel out, and u infinity and u infinity will cancel out. So this will be eta g f double dash by f dash, right, minus, so again let me do it another color. So f dash and f dash cancels out, u infinity 1 and y1 u infinity is cancelling out. So this is f u infinity g dash eta by g square, right. So now I have to do what, I have to find del v del y, but I don't want y, so I will do what, del v d eta del eta into del eta del y. Okay. So this will be what, now del eta, okay, I am writing the whole thing for the sake of your understanding. So this minus f into u infinity g dash eta by g square into del eta del y is g. Okay. So this will be what, this into, so g is not a function of eta, g is a function of x, so g into dd eta of, because f is only a function of eta, I can write this as ordinary derivative, minus, now I have here f and eta, both are function of eta, so u g dash by g square, this is a constant. Okay. And into, once I will go for f, that is f dash into eta plus f into eta dash, that is 1, okay, and whole into g, right. So that will be eta g square dd eta, okay, f double dash by f dash minus u infinity g dash, so 1 g will cancel out, so this will be g, then f dash eta, okay, plus, okay, minus u infinity g dash f, right, and by g. So be very careful, because these steps are very prone to mistakes. Okay. So let me check once again, u infinity g dash f dash by g, okay, eta, okay, and this is equal to what, by continuity this is equal to minus del u del x. So del u del x was what, del u del x was u infinity f dash g dash eta by g, right. So this will be equal to, let me write it here, u infinity f dash g dash eta by g, and I have 1 minus, right. So this whole thing is equal to this thing, so I can cancel out this and this, see, these two things are equal, right. So now that means I am having eta g square dd eta, right, f double dash this thing is equal to u infinity g dash f by g, right? Okay, I can rearrange this as 1 by f d d eta into f double dash by f dash equal to u infinity g dash by g cube nu. Now this is a function of eta only, right? A function of eta only, and this is a function of x only. So a function of eta only is equal to a function of x only, and that is possible only if both of these are equal to a constant, let us say that is c. Okay, so now let us uh, proceed with this by g cube nu equal to c. So that is what I can do, g to the power minus 3 dg is equal to c nu by u infinity dx. Okay, so I can integrate these things. G to the power minus 2 by minus 2 is equal to c nu u infinity into x, and here I will have then g will okay plus a constant, right, plus a constant, let us say c1, right. So okay, see one thing, that g is what, now I have to find this constant, right. So I need a condition. Okay, so boundary condition. Okay, so at x equal to 0, okay, and we know that eta equals to y into g, right. So I am solving for boundary layer. Okay, so g is what, eta by y, right. So I am solving for boundary layer, right. So g must be the characterization of a boundary layer thickness. Okay, so g must scale with delta, right. So this g must scale with delta, and at x equal to 0 delta is uh, sorry, g must scale with 1 by delta. Okay, because I am non-dimensionalizing this y, so g must scale with 1 by delta. So at x equal to 0 delta goes to 0, that means g goes to infinity. Okay, so and from this also you can uh, see a thing that at x equal to 0, okay, at x equal to 0 this eta should be finite, but this y should go to 0, okay, because there is no boundary layer and I am solving for only boundary layer. Okay, so at x equal to 0 this g should tend to infinity. Okay, so it is like the intuition that this g should scale with 1 by boundary layer thickness. Okay, and also if g equal to eta by y and y is the domain of the boundary layer, so at x equal to 0 there is no boundary layer, so there is no y, or actually y is tending to 0 but eta should be finite. Okay, so that means that g should be infinity. So at x equal to 0 I am having g tends to infinity. Just put this condition here and I will be getting g to the power minus 2, and that is infinity to the power minus 2, and that is 0 at x equal to 0. So c1 is coming as 0, right. So from this c1 is coming as 0. So that means g to the power, so g will be equal to 1 by root over of, okay, what, 1 by root over of minus 2 c nu x whole by u infinity, right. Okay, now see that under root we cannot have any negative thing, so from this I can say that c must be negative. So let us have Cs minus 1, and this is what Blasius took to get the Blasius solution. Okay, so let us have Cs minus half. So you can take any other thing. Okay, if you do your own analysis, then you will get any other similarity variable, but the essence will be remaining same. So I will suggest you to try with any other variable like C as minus 2. Okay, so if I take C as minus half, then I will get G is equal to nu x by u infinity. Okay, so I am getting the G as u infinity by nu x. Okay, so this is the form of G. So this is the similarity variable. Okay, so there is another method where you assume the similarity variable at the first to be this, then you just proceed through the mathematical calculation. Okay, so just see one thing, that we got delta as x into x by re x whole to the power minus whole to the power half, and that is equal to x by root under what, u infinity x by nu, and that is nothing but root under nu what, nu x by u infinity, and that is scaling with 1 by g, right? It is scaling with 1 by g. So this assumption is coming. Okay, now okay, so C we have taken it as minus half. Okay, so now let us go for this equation. So that is 1 by f, right? That is 1 by f d d eta of f double dash by f dash, and that is equal to minus half. Okay, so then I can have this f double dash by f dash is equal to minus half f d eta, right? Okay, so now let me define this f d eta integration this as a function f. So can you see something physically intuitive, that is f is what, f is equal to the velocity u. Okay, and just it is just scaled with u infinity. So I know something like a stream function psi. So psi is defined as what, del u del y, right? Yes, I can have a minus, but that will depend. You can have a minus, you cannot have a minus. If you are having a minus here, then so sorry, so u is defined as d psi dy, and then v will be defined as d psi dx. I apologize for the mistake. Okay, and you can have a minus here, then you will have a plus here. Okay, okay, so then u is defined as del psi del eta, and then what, psi is defined as u dy. Okay, this thing, right? So see that instead of u I can have an equivalent thing of f, and y is equivalent of eta. Eta is just a scaled parameter with respect to y, right? So this is, so this and this are equivalent. So this f must be equivalent to the stream function psi. Okay, so this is, so this capital F is denoting the stream function psi. So this f is like this, the similarity variable for the stream function psi. Okay, so f is not a similarity variable, but in similarity solution similarity variable is g, and f is the transformation for psi. Okay, f is the transformation for psi, just like we have transformed u to f and y to eta. Okay, so then we can have, so I am having this as f. So then small f is what, then small f is df d eta, right? Then small f dash is actually f double dash, right? because this is small f equal to f dash. So this will be f double dash and this will be what, f triple dash. Okay. So then this equation boils down to f triple dash by f double dash is equal to minus f by 2, and that is, I can rearrange this as what, uh, f triple dash plus half into f double dash equal to 0. So this is the celebrated Blasius equation. Okay. So this is the Blasius equation. So let me write it separately. So this is the Blasius equation. Okay, so now once you have got, I will give you a small mathematical homework. So I have got G as what, root over of u infinity by nu x, right, u infinity by nu x, and I also have an expression of v in terms of y, I mean eta f and g, right. So and that was, okay, that was what, this, right, sorry, that was this thing, that is I was having v equal to this, right. So just put here g equal to root over of u infinity by nu x, okay, and come up with an expression of v, okay, transformed expression. And we also have now, so your task will be to come up with expressions of u and v in terms of this, the similarity variables, okay. I mean, so I have v here, so your, sorry, you don't have to transform this g here. What you have to do is come up with an expression by transforming f equal to f dash. Just put it here. I mean, it is very not a very difficult task. And also put here f equal to f dash. So that is directly u infinity into f double dash into g dash eta by g, right? Okay. So now let us calculate other things. Okay. So our main objective was, I have told, I mean, why we are studying the boundary layer? Because we want to calculate the drag force. So tau wall is equal to what? Mu into du dy, right? At y equal to 0. So this will be what? Mu into df d eta into this into dy, and I have introduced f here, so I will have to get an u infinity here at y equal to 0, right? So now just put the values, okay. So this is what, this is g, right, and in terms of capital F, this is what, f double dash, okay. So this will be at y equal to 0 means at eta equal to 0. So this will be what, this expression will boil down to mu into capital F double dash of 0 into g into u infinity, right. So okay, now g is root over of u infinity by nu x into u infinity f double dash of 0, right. So I can do some manipulations here, so let us do that. So I can have a rho here and I can have a mu by rho, that is nu, and then I can have u infinity by nu x into u right? So I can have an u square here and u infinity. Okay, so this and this will cancel out, so this will cancel out and this will be root, this will cancel out and this will be root, right? So I can have rho into u infinity square, okay, into 1 by u infinity x by nu into f double dash 0, right? So this is this into Rdx whole to the power minus half f double dash of 0. So we got this form from the scaling analysis, but now I have got the constant here and this will be 0.332, okay, if you solve the Blasius equation by shooting method numerically. Okay, now similarly you can have the drag coefficient CD is equal to, or maybe skin friction coefficient, so let us have the drag coefficient. Okay, so this will be what, drag force by half rho u infinity square into some area. Okay, so maybe the width of the plate is b, okay, into the length of is l. Okay, so this d will be what, d will be tau into integral of b dx, okay, tau wall into integral of b dx 0 to l, and this will be half of rho a infinity square bl. So how I got this tau into b dx? So just consider okay, a plate like this, okay, and so we have to draw uh, thickness also of a finite thickness, okay. Okay, so if I take at a distance x some element dx, okay, so this x is dx and I can have this and this, okay, so this is b, so this is what b, this length is b, okay, and this total length is l, this total length is l. So this area is what, this area is b dx. So at x, if I am having tau wall, so then the df will be tau wall into area, that is b dx. So I am just integrating that, and tau wall is what, tau wall is nothing but I have just calculated, that is rho into u infinity square into rex whole to the minus half into f double dash 0, right? So let us have that 0 to l rho into u infinity square into rdx whole to the power minus half, right, into f double dash 0 b dx by half rho u infinity square bl. So rho into a infinity square, this will be cancelled out, b will be cancelled out, right? So this will be what, 2 by l, one l is there, right? And f double dash 0 will be out, and rdx whole to the power half, that will be what, nu by u infinity x dx, right? Okay, so that will be 2 f double dash of 0 by, this will be 0 to l, so root over of nu by u infinity will be taken out, and here it is x to the power minus of dx, so x to the power minus of plus 1, so x to the power half by half, right, 0 to l. So that will be this thing, so this 2 and this 2 will be 2 into 2, that will be 4, okay, by l root over of nu by root over of u infinity into root over of l, and this will be cancelled out with this, so this will be root l, and this will be what, finally 4 f all dash 0, okay, into okay, by root over of u infinity l by nu. So that will be 4f this REL whole to the power minus half. So this will be what, 4 into 0.332, that will be 1.328, right? Yes, 1.328. So many of you may have used these expressions as the formula to calculate the drag coefficient and the skin friction coefficient. So likewise, now your homework will be to find the skin friction coefficient tau wall by half rho a infinity square, and that is not actually homework. So this is tau wall, right? This whole thing. So this by rho into a infinity square into half, that will be nothing but 0.332 into 2 into Rex whole to the power minus half. So 0.664 into Rex whole to the power minus half. So what I was saying was that you guys may have used these expressions as some formula, but this was the origin of the formula. Okay, so this was the Blasius solution. And also, now let me come to some numerical part. Okay, so f, okay, so f triple dash plus f into f dash by 2 equal to 0. Okay, so this was the Blasius equation. So this is a third order ODE, right? So how can you solve this? You can break this into 3 first order ODEs. Okay, like how? So let me define f dash equal to h, okay, and what, and okay, so f double dash, okay, f triple dash will be what then, h double dash, right? Or, and that I defined as the capital H, or okay, capital H equal to this, right? So I have one equation, that is f dash equal to h, right? So what I can do is, or rather I can do f double dash equal to h and f triple dash equal to h dash. Okay, so f double dash equal to h and f triple dash equal to h dash, that is equal to capital H. So f double dash equal to h, and right, so I can put this capital H and this h into this equation, then I will have what, h plus f, right? Okay, so I want to have 3 ordinary differential equations with first order. So I have the opportunities to retain one derivative here. So let me say that, okay, so this will be h dash plus f into what, f into h by 2 equal to 0, right? Then I am having one equation as f dash equal to some small h, then I am having another equation h dash equal to capital H, right? So just see that I am getting now 3 first order equations coupled with each other, right? So I am getting, okay, coupled with each other. So now I am getting these 3 equations. Okay, so how you can solve this like this, that you have the boundary conditions, right? So this is a third order equation, Okay, so then you must have three boundary conditions. So now let us see those boundary conditions, right? So mm, at y equal to 0, I have no slip, that is u equal to 0, right? And this will boil down to, at y equal to 0 means eta equal to 0, I will have f equal to 0, right? Sorry, small f equal to 0, that means f dash equal to 0. Okay, then I can have, so this is 1, then I can have at y equal to delta, okay, yes, at y equal to delta, u is equal to u infinity, that means at eta equal to 1, okay, at eta equal to 1, this will be f dash equal to 1, right? F dash equal to 1. So let us not take eta equal to 1, because exactly we don't know that if delta is equal to root over of nu by a infinity x or not. Delta scales with this, that we have shown earlier also, okay, but we don't know that. But rather the actual boundary layer theory says that if eta tends to infinity, so these are the subtle mistakes that you can also make, okay. And then I can have what, another boundary condition. So at y equal, or okay, so let me not tell as y equal to delta, so at y tends to infinity, okay, so del u del y is tending to 0, right? So that means at eta tends to infinity, okay, u is f dash, u is f, small f, and capital F is small f dash, right? So this will be this, and this will go to 0. So then I have three boundary conditions, okay. So just see that, okay, f dash is what, f dash is h, so that means h is equal to 0 because f dash is h, okay, and here h is equal to 1, right? And h dash means capital H, so this is small h, so this is going to 0 here, okay. So for this equation, so these are three first order equations. So to solve each of these I need three boundary condition, okay. So let us solve, I mean I can solve this one, okay, and as I am having a condition for h, okay, okay, so and okay, so I can solve this one, okay, because I have the boundary condition, okay, for h, and then I can solve this one also, okay. So and then I can put the solution into this one, okay. Then I have to guess some value for f double dash, that is h dash, that is h dash. So then I have to guess some value of f double dash at infinity, okay. So that will be my guessed boundary condition, okay. So I mean I have to assume some function f, okay, and then I can calculate this h double dash, because h dash is equal to f double dash, right? So h dash is equal to f double dash, right? Or maybe f triple dash, h dash is equal to f triple dash, yes. So here I have to assume or I have to guess some value, okay, or some function of f, okay, and then if I am guessing some function of f, then I can solve for all these equations, and I am having these boundary conditions, these three boundary conditions. So two boundary condition, maybe h equal to 1 and h equal to 0. So I am repeating once again. I will solve for uh, of I will guess a value, I will guess a form of f. Okay, then I will do what? So here I will guess a value of f, and then I will do solve all these three equations. Okay, and I have to initialize these things. Okay, I have to initialize these things. So to initialize at eta equal to 0, I have h equal to 0. I have this value. Okay, so the better thing is I will show a code. I will code this thing and I will show this whole technique to you, okay, in the next class. And this is the shooting method, and I will suggest you to study the shooting method by yourself and you can solve this equation. Okay, so actually what is the method is you can assume some f double dash of 0 because you have to initialize all these equations. Okay, so you can assume some f double dash 0, then you can find f with these three ODs. Okay, then you can find f double dash. So if you can find f double dash at infinity equal to 0, and that is what this boundary condition is saying, then you are done. Okay, so shooting method is nothing but you have to solve for the value of f. So one technique is assume some value of f, okay, and then solve for these three one by one. That is, solve for first maybe this, as you have assumed some value of f. Okay, so you can solve for this and then find f double dash infinity, f double dash infinity. If that is coming to 0, then you are right. Or what you can do is, you can, as you know that you are having at eta equal to 0, h equal to 0, then you can have h as a function of small h, right? Okay, h as a function of small h, then you can solve for this and you can get f as a function of small h, and then you can solve for this, and then you can find f double dash infinity. Then if it is coming to 0, then you are right, and if it is not coming to 0, then you have to change your guess. So in the next class I will show you the appropriate scheme, okay, appropriate Blasius, I mean appropriate shooting method. So the philosophy of the shooting method is, you have to guess some value, right? You have to guess some value, and then you have to solve for uh, a target value. So here my target value is f double dash infinity. So if my target value is achieved, that is f double dash infinity is 0, then my guess was correct. But if my target value is not achieved, then my guess is not correct. Okay, so I will show the scheme in the next discussion, and then we will move into the momentum integral method. In the meantime, if you can do it by yourself by learning shooting method, then I will suggest you to code it in any language you do prefer. Okay, so until then, goodbye. So I understand that these last few things, that is the solution technique for the Blasius solution, is not clear to you. I understand that, and don't worry, I will show you the whole scheme and probably the whole code in the next class. And until then, if you have any doubt or if you have any suggestion for improving these discussions, you can always post it in the YouTube comment. So, and take care, and just tell me in the comment if I can help you in any of your life aspects. Okay, so until then, goodbye and take care. Thank you.